Hello, Lahore. My name is Joseph Hound, and I'm going to be giving a topology crash course. I'm one of a few graduate students who are going to be giving some introductory talks this year. I come from Claremont Graduate University, and I'm presenting material on behalf of Bahar Acu at Pitzer College. Our schools are right next to each other, and we've worked together on topological material before, so this is exciting. Here are some relevant texts for what I'm going to be going through today. Topology by James Moncrief is a classic. I'm using the second edition, and this is going to be for the first sections where we go through point set topology. I'm also going to be using some of Introduction to Smooth Manifolds by John Lee, also second edition. And this is a much larger book, and it is packed with all of the theory that you need for smooth manifolds. It is very robust, right? Another book that I found helpful is Foundations of Differentiable Manifolds and Lie Groups by Frank Warner. We won't be going through as much of this text, but if you wanted to have another text on the side, this would be a useful one to have. This is our roadmap for this talk. We're going to start here with points and sets. Points and sets are going to be how we define what a topology is, and that's going to inform everything going forward. Once we have a topology defined, we can start talking about how we've defined these open sets on our set of points and describe topological properties. We're going to talk about connectedness, we're going to talk about compactness, and we like topological properties because these are the things that don't change under homeomorphism. Homeomorphisms are going to be the maps between topological spaces that describe two topological spaces being the same. In the same way that a vector space, we can have an invertible transformation from one vector space to another, and it preserves the dimension of that vector space in a way. Or in geometry, how we use angle-preserving, area-preserving transformations. Homeomorphisms are going to be the transformations that preserve what we care about for topological features. So these topological properties and these homeomorphisms, after we talk about those, we can have a nice, robust definition of manifolds. A manifold is a special kind of topological space. We'll describe the properties necessary to understand a manifold. And the homeomorphisms are important because manifolds, if you look closely at them, resemble real space, and this informs exactly what that means. Once we talk about manifolds a little bit, we can start talking about the features that are more unique to manifolds, such as tangent spaces. If a manifold is embedded in some space, we might care about the space of all vectors that are tangent to the manifold at a given point. If we take all of those points together and look at all of their tangent spaces, we get the tangent bundle. So we'll talk about tangent bundles. Also for manifolds, we can talk about k covectors. So these tangent spaces, these are linear algebra objects. So through the tools of linear algebra, we can talk about a vector space, we can talk about its dual, and a covector is going to be something that takes a vector as an argument and it outputs a real number. So we're going to get to talk about this for a bit. And then we make a bundle out of these kinds of k covectors, and this is going to be what gives us our differential forms. So these bottom four things, using the tools of linear algebra, we can simplify a lot of the structure of studying a manifold. So, as I said, we're going to start with point set topology. How are we building up all of this theory? Well, we're going to start off with sets that have points in them. Right? Now, these points can come from a variety of different kinds of spaces. We can have some real space that looks like R2 in this case, but it can be Rn, or in the complex setting, we can have Cn, right? Points in some kind of space like this. It might be elements of a function space. So if you want to look at functional analysis, which isn't related to this talk in any way, but if you wanted to look at functional analysis, you'd be dealing with spaces that look a bit like this. And another kind of topological space that you might be worried about the points in might be a graph. You can study topology on a graph network like this, and there are interesting things that you can do here. So these are the points that we might deal with, and we're going to talk about sets of these points. What a topology is a family of subsets that satisfy these three axioms, right? So we have some space of points x. So in the real setting, we might have R2, and these are the points that we can choose from. We can choose like any of these, right? But the topology takes subsets of these, right? So some circle, like blobbish thing down here, that's going to describe some kind of set. For the topology, we need the empty set to be a member of the topology. So if I don't select any of these points, then that's going to be in the topology tau. Also, if I select every single point, if I just take the entire blob of R2, that makes one set, and that's also going to be in the topology. Additionally, if I take any sets, any collection of sets, so if I take this set, and I take this set, and I take this set, if these are all in the topology, then their union is also going to be in the topology. So this set, like that combines all of these, this set of points, is also going to be in the topology, as long as each of these individual sets are. And this is for arbitrary unions. This can be an uncountable set of, an uncountable collection of sets. It can be a finite collection of sets, any arbitrary union. We also have this third property, that finite intersections of sets from the topology tau are also in tau. So if we have these two sets, the set of points that are shared by both of those open sets, that also makes an open set with respect to this topology. And this example is with 2, but by induction you can have this apply to any finite number of open sets. So finite intersections of sets from the topology are still in the topology. This foundational material is coming from Muncre's Topology 2nd edition. And usually when we describe these sets that are a member of this topology tau, these are our open sets. This is the way that we think of these. All of the open sets on the number line, A to B, these are going to be open sets in the standard topology of the real numbers. So this is sort of what we're working with. This is the intuition behind this. First, a basis for a topology is another family of these subsets where instead of satisfying these three rules, what we're trying to do is construct all of the sets that satisfy these rules. We're trying to construct the entire topology using a simpler set, using a simpler collection of sets. So we want to find some collection of open sets such that we can represent the whole topology just by unioning these sets together. So back to the standard topology on R, the basis of this topology is all of the open intervals. So any two numbers in the real number line, if you have that open interval, A to B, that is going to be an open set. That's going to be in your basis. To construct the topology from a basis, we take all unions of these open intervals. Right? So everything in our basis, if we just take unions of all of these things, this describes every open set. Now, this is an arbitrary union. So this is for all I in some indexing set I. This can be the entire real number line. We can have an open interval that says everything from -1 to 1, and we can have the open interval that says from 0 to 2, and the open interval from 1 to 3, and so on and so forth. That can be an infinite set. And if we union all of that together, what I've just described is now the interval from -1 to infinity. So we can describe all of the open sets in the real numbers in this way. And this makes a new family. All of these unions makes the topology. If we go through, we can verify that the empty set is a member of this topology. We simply take the open interval that starts and ends at the same point A. There's nothing in that because it's open. We can verify that the real numbers, the entire real number line, is a member of the topology because we can reconstruct it using the strategy that I described a moment ago, where we have from -1 to 1, right? And we have the set from 0 to 2. And we keep doing this infinitely that direction. Well, we can go this direction as well. We can say the set from -2 to 0, right? And we can keep this process going this direction. Right? So this will make a collection of subsets. And so we can reconstruct the entire real line from our basis. And so that's going to be in the topology. We can leave finite intersections and verifying that those are a member of the topology, those belong to the topology, as an exercise for anybody listening. For another example, any metric space can have a topology induced by that metric. So if I have 2 points, P and Q, and I have some metric that tells me how far apart P and Q are, then I can describe open sets based on this distance metric. I can say that this is a point P, and I would like to consider all points that are within this epsilon radius of my point P. Right? So this defining an open set induces a topology, as long as I'm working with a metric space, which requires this distance metric to satisfy some nice axioms. This is another convenient kind of topology. We'll be using that a lot, probably. There is a useful feature of the real numbers where the rational numbers are dense in the real numbers. And what this allows us to do is induce the standard topology on Rn by only using a basis of balls centered at rational points with rational radius. So this set here, this collection of sets, these are the points y in Rn where the distance between x and y, x is a center point centered on a rational point. The distance between x and y is less than some value r also a rational radius. So this collection is described with n+1 choices of rational number. Since the rational numbers are countable, then this whole collection is also countable. A topological space that has a countable basis like this is called second countable. We're going to need that later for manifolds. Now we can talk about what makes different topological properties. Our topology is made out of open sets, and different properties related to the points in those open sets tells us which properties are going to be topological. So the first of these to talk about is going to be connectedness. So the idea of a space being connected comes down to whether it can be separated. So this is much easier to show visually. A topological space is separated if it is the disjoint union of open sets. And a connected topological space cannot be separated. So let's look at this one. This is a connected space. If this is the entire space X, just this like wobbly figure 8 thing, if that's our space, and these are the two open sets, X cannot be written as the disjoint union of two open sets because this has some stuff in between it. Right? If there is a closed set, that works. So if we outline this green and we have that be a closed set, the complement of this blue set, well, X can clearly be written as the union, as the disjoint union of this open set and its complement, which is a closed set, but it's not an open set, so that doesn't count as a separation. Right? So this is connected because it cannot be written as the disjoint union of open sets. Here's an example of something that's not connected. Two open sets, it's the disjoint union of those, assuming that these two separate components are our entire space X. And then here's a third example. This is also connected. We are allowed to have two disjoint open sets, but the entire space here cannot be written as the disjoint union of these open sets, because there are things that you're going to miss if you only take the union of these two open sets. And so this is connectedness. This is a topological property because it is based on the behavior of points within open sets and the entire topological space understood through the lens of these open sets. The next one that we want to talk about is compactness. The idea of compactness is that if I take any open cover of my topological space, I can take a sub-collection of those sets for that open cover, and a finite one at that, and still cover the topological space. So to describe an open cover, it's a collection of open subsets such that their union is the whole topological space. So if I have this topological space X, and I have a collection of open sets, so here's some open set, and here is a different open set, and here is a different open set. If I continue doing this, and I cover the entire topological space, then this is an open cover of my topological space, and then one in the middle for good measure. So those green circles that I just drew cover this, and their union is the entire space. So that is what a cover is. And if a subset of this, a finite subset of this, also covers the topological space, that's the thing that we're looking for. But we need to make sure that that applies to every open cover. Okay, so to explain that through example, the closed interval is a compact subspace of the real numbers, but the open interval is not. There are different ways to prove this. One that I like is to cut this in half repeatedly and show that eventually you're converging to a single point, which must be a compact set because it can be covered by just one open set. So to write this out, we have 0 to 1/2, union 1/2 to 0. This is just a sketch of the proof. I won't go into full detail here. If this is not compact, then one of these has to not be compact, because if they were both compact, then this is two different finite numbers added together, the number of open sets required to cover both of these, and so the whole thing would be compact. So for this to not be compact, one of these has to not be compact, and let's say that it's this one. So if this is not compact, then let's try to write this one. We're going to write this one 0 to 1/4, union 1/4 to 1/2. Okay, well now we have a smaller set, and exactly the same argument is going to apply. We're going to ignore this continuing down. Continue doing this, and this process converges to just one point. But a single point has to be compact, and so if you continue dividing this in half, asserting that one of these things is not compact, eventually you get something nonsensical. There are other theorems and whatnot that really make that proof work, but that's the spirit of the proof that I like for this. Considering the open interval, on the other hand, it is not the case that every open cover has a finite subcover. It is possible to cover this with finitely many open sets, clearly, because 0 to 1 is an interval, it's an open set, and that covers that. But if we consider instead this cover, where a sub I equals 1 over I to 1, then we look at this range from 0 to 1, and if I equals 1, this is empty. Okay, so if I equals 2, then we're dealing with the open set from 1/2 to 1, right? And great, so a sub 2 gives us that. A sub 3 is going to give us from 1/3 to 1, right? It's going to give us a slightly larger interval. And if we continue doing this, we're going to get closer and closer and closer to 0. If we take the union of this infinite sequence of these sets, we rebuild this interval from 0 to 1. Every point from 0 to 1 will eventually be hit by one of these sets, so it must be a part of the union. However, there's no point that we can stop. At no point are we allowed to say, I actually don't want the rest of this infinite series, because otherwise we're missing stuff that's arbitrarily close to 0. So there's no finite subcover of this, which means that 0 to 1 is not compact. Right? So that's the idea of compactness. It is stricter than it at first appears, but since it is defined in terms of open sets, it means that it's a topological property. We've defined it based on what our topology allows. So let's look at some other topological properties. We are going to need separation for later for talking about manifolds, but this is the idea that points in your topological space are in different open sets, right? We'll talk more about that in a moment. First and second countability of a topological space, that's another topological property. And we showed that real space is second countable when we showed that it had a countable basis. So that's one of these topological properties. It's based on open sets. Metrizability, the idea that the topology can be induced by some metric, that's a topological property. There's also this notion of paracompactness, which is more like a local behavior of compactness, and it's more important for the theory of manifolds than compactness is, really, but we're not going to get too much into it. Once we start talking about manifolds, there are other topological properties that are more specific to manifolds. Genus, the number of holes. Betti numbers, more general than the number of holes. We can talk about the number of voids trapped, like a sphere has some points like trapped by the outside that we don't really have access to. It's not in the topological space, it's just a trap, right? That's reflected by Betti numbers. Homology groups also related to Betti numbers and genus. It depends on your homology. There are a lot of different ways to construct these kinds of groups, but those are topological properties. Cohomology, homology but backwards, those are topological properties. Orientability, a Mobius strip is not orientable, and so if we map that to another topological manifold, and we map all of our open sets in a coherent way, then that's a topological feature. It's going to be preserved. So these properties are preserved when we're mapping one topological space to another, if the way that we map them is between equivalent spaces. So what we need is this idea of a homeomorphism, right? Homeomorphisms are the way that we're going to map equivalent topological spaces together. So what is a homeomorphism? What are these maps that preserve our topological properties? This is what we need. We need a map from two topological spaces, and we need it to be bijective. We need every one point here to map to one point here, and vice versa. We need that map to be continuous, which we'll define in a moment, and we need the inverse of that map to also be continuous. And that's going to give us everything that we need. Continuity is doing a lot of lifting here, because continuity is the part where we map open sets to open sets, and we ensure that our topological structure is preserved. If we meet these conditions, though, we call it a homeomorphism. This is an equivalence relation for topological spaces. It is the one that matters the most. It's the one that hits at the real foundations of your topological space. There are other equivalence relations that you can use in other contexts, but this is the one that we care about here. In the same way that in geometry, we use translations, rotations, reflections, the kinds of transformations that don't change your volume, they don't change your angle. It allows us those kinds of transformations that allow us to map equivalent triangles together. This is the universal transform tool. Oops. In the software that I'm using. If I take this and I rotate it, right, that is a transformation that did not change its volume, and it preserved the angles of this figure. So in geometry, that is the same shape. Right? In linear algebra, we want linear transformations. We want invertible linear transformations to make sure that the dimension of our vector space is the same. We can make a translation from one basis of one vector space to another using these linear transformations, and that accomplishes everything that we need. Everything behaves nicely with the basis of a vector space, and with a linear transformation, the linearity properties, scalar multiplication, and the addition of vectors, everything just works. So here, the fundamental thing that we need is homeomorphisms. Homeomorphisms because we need to make sure that open sets get mapped to other open sets. We need to make sure that we preserve all of the properties that are built from this idea of open sets. So here is an example. The real numbers to the positive real numbers. If I take x and I map it to e to the x, well, this is a bijective function. If there are two different values that I target, if e to the a is equal to e to the b, a has to be equal to b, right? There's only one number that maps to any given number. And also there's an inverse, and so for every y in the positive real numbers, there's some value x in all of the real numbers, such that we have e to the x equals this y. We take the inverse, the logarithm. Right? So we know that this is bijective. That just works. It is continuous. Continuity understood in the normal kind of sense here. And the inverse, the natural log, this is continuous on the domain of the positive real numbers. So that makes this a homeomorphism. Right? If I take an open set in the real numbers and I look at the image of that open set under this map, I'm going to get another open set back. So all of the topology that I do here carries over to any topology that I might want to do over here, and vice versa. So for functions from the real numbers to the real numbers, we usually first talk about continuity in terms of being able to lift your pen off the page, or for a pre-calculus or calculus course, we talk about delta epsilon proofs. The more general setting for this is if we have a function from one topological space x to another topological space y, if I look at an open set of y, I want the preimage of that open set to be an open set of x. Right? That's the thing that I'm looking for. So open sets are mapped into by open sets. Right? If I look at a graph version of this, here is a continuous function. I have this open set on the y-axis that I'm mapping into. What maps into that open set? Well, it is another open set, right? So this is a continuous function because this property holds for every open set that I could map into. Here is a not continuous function. It does not hold here. This point right here is closed, and so this interval right here, the set of x that's going to map into this interval, that's not an open set. It's half open, right? So this is our expanded notion of continuity. This is the property that makes sure that our open sets are getting mapped correctly. Right? Here is another homeomorphism. This is the stereographic projection of the sphere. If I take the map from the sphere, subtracting the North Pole, right, and this is just the standard unit sphere, and I map that to the real numbers according to this map, where I draw a line from the North Pole through every point in the sphere, well, whatever point in the sphere that I'm mapping, and I continue that line until it intersects with the plane where z equals 0, then I map it to this point here. Whoops. And by mapping it to this point, I have created something that is bijective. It is continuous because we're taking out the North Pole. Z cannot be equal to 1, so it is continuous on its domain. And also, this is invertible. and the inverse is continuous. I won't prove that, but it is true, and you can check that out yourself. So, since it satisfies those three properties, this is also a homeomorphism. So, if I take any open set on the sphere without the North Pole in it, and I follow this map, I'm going to get an open set in the real plane. So all of these topological structures, all of these properties, any topological structure that I have on the sphere without the North Pole in it, is going to carry over to the real plane, and vice versa. I can do one thing and then translate it and then translate it back. Everything works out just fine. All right. So with the idea of a homeomorphism defined, we now can tell you what a manifold is. So everything so far has come from Muncre's, and this is also going to come from Muncre's, right? So this is the definition of an M manifold. It's a topological space, and it has these properties. One, it is Hausdorff. I will define that in a moment. It has a countable basis. I described what that was before. We can talk about that again in a second. And also, each point has some neighborhood which is homeomorphic to an open subset of R to the M. This is the part of a manifold that lets us say that it looks like real space. So we'll talk about that in a second as well. All right, so we have the definition of a manifold. Let's go through these properties real quick just to make sure that we understand everything that's going on here. The first of these is Hausdorff. Hausdorff is a topological property, and it is among the separation. It's among the separation axioms. If a topological space has this property where they can be surrounded by open sets that are disjoint, containing any 2 points that separate those 2 points, then we call it Hausdorff. Right? So here's a picture of this. Here's my topological space X. I have this point X. I have this point Y. There's some open set that I can put around Y that does not overlap with the open set that I put around X. Right? There's no overlap here. So this is separable in the Hausdorff sense. There are other separation axioms. We don't need any of those right now. But the real numbers, real space, has a lot of useful separation properties for working with manifolds. We just don't need it for the definitions that we're working with right now. So the other property that we need, a countable basis. The reason we want a countable basis is it's important to work with metric spaces. If we have a countable basis, then we can induce a topology with a metric on our topological space. There is another grad student, Darius, will be talking more about metrics, and metric spaces are probably going to come up in that. But the reason we need a countable basis is so that we can have a metric space. Right? Additionally, if we want to study the geometric properties of a manifold, we need there to be metrics. We need to describe things like lengths, areas, volumes, curvature, that kind of thing. Those require metrics. So we need a countable basis. The third thing, that locally it looks like R to the M. This is the part where we say that every point in the manifold has some neighborhood homeomorphic to an open subset of R to the M. So it's not all neighborhoods of a point. After all, the entire topological space is an open set that contains our point. But we can choose some. There's something small enough is usually the way that we think of it, where it is going to be as basically flat as we need it to be. Okay, so if we look at a sphere, this is the 2 sphere. If we look at a small open set around this point, this is the point that I am talking about, right there. Then there's some homeomorphism that will take us to the real numbers, right? Not to the real numbers, to the real plane, right? There are 2 dimensions on this surface, and we can kind of see that, like, if we step outside and we just look at the sphere around us, just the surface of the Earth is the sphere. It looks flat. This looks like a flat kind of space because we are looking at a very small open set. So that is the part, that is a feature that we get from the third criterion of a manifold, that every point has some neighborhood that is homeomorphic to some open set of R to the n. And in this case, it's R2, but the same rule applies to any number of dimension. So if you have the 15 sphere, same rule applies. It'll just look like 15-dimensional space. So one of the reasons that we like this is that it tells us that a manifold can be embedded in some real space as long as we have enough dimensions for it. So the n sphere Sn, that's a manifold, and we usually construct that by embedding it into one more dimension. We look at the unit ball in n+1 dimensions, and we look at just the surface of it. So if we have this function in n+1 dimensions, and the output of this function is to square everything and add everything together, if we then filter that down to just the set of points where this function evaluates to 1, then we've defined a hypersurface in n+1 dimensional space. That hypersurface is the standard for Sn, right? So that's a manifold. It's constructed by this embedding, and there is some number of dimensions where this manifold embeds in that real space. Another example is the Klein bottle. If you don't know the Klein bottle, it is sort of a surface that is taking a Mobius strip and closing it so that there isn't a boundary to it. And it has this non-orientability property, and it's a surface, but if you walk around on it, eventually you end up on the inside of it, and it doesn't like really enclose an area. It sounds not very physical, and part of that is because it cannot be embedded in R3. We couldn't build a Klein bottle that doesn't involve intersecting itself. But if we embed it in 4 dimensions instead, this is the number of dimensions that's required to have a faithful embedding of it where it doesn't self-intersect. So there is some number of dimensions where this manifold embeds properly. These are the properties of a manifold, and this is why we like them, right? We need a countable basis. We need them to be Hausdorff. We need to be able to separate the points on our manifold into different open sets. And we need it to locally look like R to the n, right? We need it to look like real space. The definition that we've just given is not quite general enough to do everything that we want to do with manifolds. And so we have a little bit of a problem here. And it's an easy fix, but we do have to go through the work to fix it. So if we look at this torus, and we take a bite out of it, and we don't include any of these boundary points in the torus, if this is our topological space and it doesn't have any of these points in it, that is a manifold. If we zoom in close to the boundary, every point can have an open set around it that does not intersect with that boundary from the separability from being Hausdorff that we talked about before. So this is a manifold. This works just fine. But this is not a manifold. These are very similar kinds of things. The only difference here is that here we have this boundary. And the problem is that if I choose a point specifically on the boundary, then there's not a neighborhood that is contained entirely within the manifold. So there's not going to be an open set that's homeomorphic to an open subset of real space. What we have to do is we have to replace property 3 with this property where each point has a neighborhood homeomorphic to a half space. So the problem here, if I zoom in, here is an open set around this point. My color coding is all over the place here. Here is my point on the boundary of this boundary on the torus. If I have an open set, I have something that isn't homeomorphic to real space, right? Well, what if I just relax my condition that I have to be homeomorphic to real space? Instead, what I want is that my neighborhood is homeomorphic to an open subset of the half space. So it's the same as real space. The only difference is that that final coordinate has to be greater than or equal to 0. And that's it. So now, if I look at this point, now that is clearly homeomorphic to the real half space in 2 dimensions. Like if I just make a coordinate system here, like everything here, this is the half space, and I have a point that looks just like it belongs right here. Right? The openness of this subset is maybe in question, because if you look at this and you're new to this idea of thinking of things in terms of their open subsets, you might think, well, that's not actually an open subset. And you are kind of right. It is not an open subset relative to R2. Right? It is an open subset relative to this half space. If we restrict our space to just this, this is now considered open. This is the subspace topology. The subspace topology is something that we would cover more if we were working through Moncrief's. Though here this definition occurs in Lee, the Introduction to Smooth Manifolds book. So the openness of a set might not be the same when we're talking about subspace relations. All right. So this is a manifold with boundary. The interior points, the parts that are above this half plane, that still works just like a manifold. And then this lower part, the part where that final coordinate is 0, well, now we have a different structure to be working with. And so this is a category that lets us work with manifolds with all of their nice structure. Many things carry over just fine. Tangent spaces work just the way that you would want them to. But we can describe more things. This is general enough for us to work with more useful things. And here's just a quick comparison. S2, the outside of the sphere, that is a manifold. It is 2-dimensional, and it does not contain the center. Right? The manifold with boundary that we might think of when we think of spheres early on. Like if this were a solid wooden ball, this is the 3-dimensional ball. It is 3-dimensional. It is the same shape, but it has all of the inside points too. It does contain the center. Right? This is a manifold. This is a manifold with boundary. So it's a slightly different category. We can express some things a bit differently, and we get more nice structure out of it, and we can still use all of the nice structure of a manifold. Here is a nice property that just also capitalizes on a boundary. If we look at 2 manifolds and we want to glue them together, we can make boundaries, and then we can glue them together on these boundaries. Right? We won't need this property here, but this is just another reason that we might like to have a manifold with boundary as the default category that we work with. Another useful thing when we're working with manifolds, since we know that they can be embedded in real space, we can think of these as hypersurfaces in some ambient space. And if we look at one point in our manifold, we can think about the vectors that are tangent to our topological space at that point. Now, in the case of a surface, all of those possible tangent vectors make a 2-dimensional space in alignment with the 2-dimensional surface that we're looking at. Here is a 1-dimensional manifold, just the circle. This point here has a tangent line. Right? Tangent lines to circles are also a tangent space at that particular point. And this is a subspace of this ambient space R2, but when we're working with manifolds, we don't have to work with an ambient space. We could do that, but some of this comes down to intrinsic properties of the manifold itself. And if we're doing topology on open sets just with our manifolds, we would like to be able to take advantage of as much structure just from the manifold as possible. And this starts off our discussion of tangent spaces. If we look at a point in Rn, if we look at just a vector space, then we can describe tangent vectors by reference to another vector space. So this might look a little bit strange, but this point P in this vector space R2, imagine I staple a vector space right here at this point. And this point is the center of that vector space. Right? That's the origin. That's the 0 vector. And every vector in this new vector space is described in relation to this point. This is the type of tangent space that we're going to be making, right? So every point in R2 is going to have its own tangent space, right? So here, that's going to have its own tangent space. This copy of R sub P, but R sub Q over here, I guess, this is different from this R sub P, R2 sub P. So in Lee, in Introduction to Smooth Manifolds, he calls this a geometric tangent space. I don't know exactly why it's geometric when we're dealing with the vector space setting and it's not on a manifold, but it is nice to get our mind around the idea right now that all of these are different vector spaces, right? The vector space at P is different from the vector space at Q. It's just that in the vector space setting, these are all the same rough shape, right? Like there's a we can use the basis vectors of R2 for this vector space as well. We just say that it's P plus E1, P plus E2. These are the basis vectors of R2 sub P. And the same thing for this vector space over here. If we move our setting to a manifold, a general M manifold, we assume the same kind of structure, right? Every point P is going to have its own tangent space. This is just something that we can define. We can use differentials on smooth manifolds to describe these, but it is its own algebraic object for a lot of purposes. So there is this idea of smoothness. We're going to skip over it. There is a good amount of material from the Foundations of Differentiable Manifolds and Lie groups, the Warner book I mentioned, that describe what makes something smooth. Right now, I'm just going to throw this picture at you and wave my hands at it. If we have some open set that is a chart for this manifold here, and some other open set that is a chart for this manifold here, their intersection is going to be some different open set that's on the manifold. And what we need is for any function defined on either of these two sets to agree. So if I describe a function on this manifold, I need to make sure that any value that I assign in this yellow band is the same whether I'm looking at it while it's green or while it's red, right? I have to be able to output the same value. And if we have these kinds of properties, another important thing to talk about is partitions of unity. This is the kind of property that lets us describe a global function that all outputs 1. So that every point on our manifold is covered with this value from this function that just outputs 1. And it's described for each of these different charts. The reason we like that is because then we can just multiply that by whatever function we need. We have some base function that we're working with, and then we can describe any other function on the manifold by modifying that partition of unity. That is all the detail that I'm going to go into for the purposes of smoothness, because this gets really dense really fast. A lot of calculus. Now we're going to look at a different way, well, it was different to me when I learned it, a different way of writing our vectors from the tangent space. Typically, at least for me, I understood vectors in terms of ordered lists like this. 1, 2, 3, that tells us the coefficients in each of the 3 coordinates for a 3-dimensional space, in each of the 3 directions, I mean. And so that tells us where this vector is pointing. Another way that we can see it is with basis vectors like I, J, K in a physics context. These are the basis vectors for a 3-dimensional space. and the coefficients tell us the coordinates. Those are the coordinates for this vector space. Here we're going to do the same thing, except our basis vectors are these. These partial derivatives with respect to x in all of the directions for each dimension of our manifold, this is our basis, right? So now our vectors from the tangent space have coefficients based on whatever vector we're dealing with, but they're always multiplied by these different partial derivatives. So we have some linear combination of partial derivatives, and that allows us to treat our vectors as operators. Each of our vectors from the tangent space is then going to act on functions, it's going to act on vector fields, and we can use these as operators in a lot of different contexts. And it makes the directional derivative a lot easier to visualize and a lot easier to work with. At each point in the manifold, we now have these tangent spaces. They have basis vectors of the partial derivatives in each direction. But what happens if we map our manifold to a new manifold? What parts of the tangent space get carried over? Like if I have this manifold, this purple one, and I map it to this green manifold, I have this tangent space at a point P, right? Well, if I take a vector from this tangent space, what should I expect it to look like in the tangent space of y? Like, how should I be able to make this map in a way that makes sense? And this is the way that we do this. We're going to define the differential. If we have a function that takes us from x to y, the differential of f at p takes us from the tangent space at p to the tangent space at f of p. So p under f is going to get mapped to some other point in our new manifold y. That new point has its own tangent space. So this tangent space is now going to map into this tangent space. And the way that we map any vector from this tangent space to a vector from this tangent space is using this vector as a differential operator, and we want to obey this relation. We want to make sure that if we apply this vector, if we map this vector and apply that to a function on the new manifold, it holds this relation. It's the same as if we applied that as a differential operator to the composition of our new function with the mapping function. So when we follow this map f from x to y, if in this example it's from the unit circle without the North Pole to the real number line, we have this point P. This is going to get mapped under f to f of p. The tangent space at p, tpx, there's some vector here, right here, and that describes a differential operator because this is how we're representing our vectors. What we want this to get sent to is the element of the tangent space at f of p of this new space such that this relationship holds. We want the differential operator applied to the composition g of f. So any point that we have in the circle, we apply f, see where it lands, and then we apply this new function. We can apply this as a differential operator to this function. That gives us a new differential operator, and that can be described in terms of this tangent space. That is what we want to map to. Those kinds of computations are easier if you are given a specific point and you know a specific function in the new space that you're dealing with. In a more general setting, we want to work with tangent spaces as their own algebraic object or topological object. So we're going to create what's called a tangent bundle. First, I want to emphasize again that all of the tangent spaces, t sub p of x, these are their own vector spaces. Every point of the manifold P has its own tangent space. So all of those are different tangent spaces. If we take the disjoint union of all of those for every point in the manifold, that is the tangent bundle, right? If I have two different points, these have two different tangent spaces, but I can take the big collection of them, this big union of all of these possible tangent spaces across all of the points of the manifold, and that gives us the tangent bundle. Now this is a much larger space. We now have twice as many dimensions, and here is another way of looking at it. If we have this circle, S1, we have this point, we have this tangent space. Instead of looking at this as a tangent to a circle, we can just treat this as its own vector space and kind of look at the cross between this real number line that this is isomorphic to and S1. So if you look at this cylinder, you can see how any point that's on this circle has a corresponding vertical part that gives us the shape of the tangent space at that point. So this tangent space, this T sub P of S1, this includes into this cylinder. If we interpret the tangent to be not a tangent to a circle in a geometric kind of setting. When we look at this, we sort of see that this is also a manifold. We can see that any of the vectors that we choose above this point, this is in a way very similar to the vectors that we might choose for a nearby point, as long as we are working with a manifold that is sufficiently smooth. Like, we need these notions of smoothness for this kind of thing to work. But if we have that, we have a manifold here. And so this is a useful object to be working with. If we have this as a manifold, we can look at subsets of it. So let's talk about vector fields. If you know what a tangent bundle is, we're dealing with this larger space. We're dealing with all of the tangent spaces at the same time. From each of these tangent spaces to each of these points P in our manifold, we just want to choose one vector. So here is another picture of this circle, and I've just drawn haphazardly some vectors that are tangent to this circle. Here is the way of drawing that as a section of that cylinder. You can see that some of these are pointing in the positive direction. I just chose this to be the up direction on this cylinder, and some of them are pointing backwards. But we can create this kind of shape. If we have this in a continuous kind of fashion, we have a continuous vector field. And this is a really nice object to work with. This loop in this larger space of this cylinder, this is a nice thing to work with. More formally, we call these sections. The idea of a section is that we have some way of projecting from a larger space to the space that we want to look at. We want to assign elements of our larger space to our smaller space, the base space, in such a way that when we project, we get back to the point that we were mapping from. Since we can always choose to just forget the information about this vector and map back to the point P that generated the tangent space that vector lives in, we get this projection for free. And so this makes this mapping a section. This association of each point in the manifold to a vector in its tangent space, that vector field that we're generating, that is a topological section. Sections can be more general than this, but in the vector field, in the vector bundle setting, it's easier to visualize, although you can have a section of different kinds of algebraic objects as well. Now that we have tangent spaces associated to all of the points in our manifold, we can start using other linear algebraic structures to make sense of this. And the direction that we're going to go now is to expand to tensors. The idea of a differential form is based on maps which accept some number of vectors and then output real numbers. So we're going to start with the vector space setting. We describe an exterior form on a vector space as an alternating covariant k-tensor. So the part where we say that this is a k-tensor says that it is going to accept k vectors. If you have a 1 through k, this is how you're going to enumerate your vectors. You're going to feed this into a function. Covariant, this describes what happens to the tensor under a change of basis. And alternating is this property where if you change the order of your vectors, then you're going to be flipping the signs. It carries some other structure with it, like if you put in the same vector twice, you're going to get 0. But we won't go through all of the properties of exterior forms. This is just light coverage. So again, functions, they're going to take k vectors as inputs. They're going to output real numbers. An example is the area form. So this is a 2 form, k equals 2. We have omega of vectors u and v. And what we're going to do is we're going to take the first coordinate of u, second coordinate of v, minus the second coordinate of u times the first coordinate of v. And you might recognize this as the area of the parallelogram spanned by these two vectors. Right? So this is some mapping, which takes 2 vectors, and it outputs a real number. And that is that's a k covector. That's a 2 form, and it is alternating, and it is covariant. Other relevant forms, we can talk about volume forms. If you want a generalization of this, you can talk about the volume of a parallelepiped. And symplectic forms are also common. Overall, all of these kinds of forms take on the structure of a vector space. So when we see capital lambda to the k, v star, v is the vector space that we're dealing with. The vector space that we're going to eat vectors from. The star denotes that we're dealing with the dual of this vector space, and the dual being the collection of all of the vectors from the dual space, which are covectors. These eat one vector at a time and output some number. Canonically, you match these up with the basis vectors from your vector space. Lambda to the k tells us that we are dealing with something that is going to eat. We're dealing with k covectors at a time. We are going to eat k different vectors and output our number. It's going to be some relationship among all of these. So this is the linear algebraic structure. Now we want to look at this in the context of topology. What about on some arbitrary manifold? If each point P has its own tangent space, then this dual space is going to be different for each point in the manifold. And so this algebra that we have of these k forms is going to be acting on different spaces, right? So we have to make sense of that. The alternating covariant k tensors for each of these tangent spaces, these all have the structure of a vector space. These lambdas to the k's, these have the structure of a vector space. And we can use this to form a vector bundle in the same way that we did with the tangent bundle. To every point in the manifold, we are going to associate one of these vector spaces. And it is this vector space, exactly. So to the point P, we're going to associate this vector space. For any particular P, we can know what this looks like. For any particular P, we know what the tangent space looks like. And so we know what the dual space is going to look like. And then we can look at all of the tensors on that dual space. Right? So for any choice of P, this makes sense. It is when we look at it for the entirety of the manifold and we do the discrete, we do the disjoint union of all of these. That's where we get the bundle of all of these k forms. Right? And this is how we denote that. These are the k forms defined for the entirety of the manifold. Right? This is a bundle, and this is where all of our k forms are going to come from. In the tangent bundle setting, we took a section of it to describe a vector field. Each of the vectors from the tangent bundle could be used in the to associate to a point in the manifold. Right? We can describe any vector field we want with that. Here, we want to describe any k-form in terms of what it does to a point in the manifold. Right? So each point is going to have its own tangent space and its own k-form associated to it. Right? And that is the section that we choose. Right? The section is the part where we choose just one thing from each of these spaces to associate to each point of the manifold. Right? One k-form per point. And that is a k-form on the manifold. Right? So here, there's a lot of mapping going on here. So here is a picture that is hopefully helpful. I take a sphere. Right? This is just my stand-in for some topological space. Right? So from the tangent space, I can choose vectors. Right? So from this tangent space, let's say that I choose k of these vectors, and I now have this list of green vectors 1 through k. Okay. This does not have to do with the k-form on the manifold. That is not what this is. All this is the elements from the tangent space that are going to be eaten by the k-form. Okay. On the right, this is the k-form. For one point, we have some vector space, kind of like the tangent space, and so I've drawn it in a similar kind of way, but it's not the tangent space. It's a vector space with its own structure. We choose one element from it for this particular point P, right? And so I'm going to call it omega sub P, omega being a normal variable, like a typical variable for these types of k-forms, and then sub P to indicate that this is specifically the form that is associated to that point P. That's my choice for this point P. If I take this form and I feed it these k vectors, it's going to output a real number. And that's why I spent the time to describe these k vectors coming from the tangent space, because this is the space that this form eats things from. Right? So the k form defined for the entire manifold, we're going to have this omega sub P for every point, and for every one of these points, if we had vectors associated to those points, it would eat those vectors. Right? That is our choice. The choice of omega sub P acts on these vectors because that's what tensors do. And the choice that we make of omega P for what it does with those vectors, that is what defines our k-form. So our k-form is defined by the choice of this omega sub P for all of the P and X. And this should be continuous in P. I might have specified that earlier, but omega, for P and Q close together, omega sub P and omega sub Q should, if we map the tangent vectors to each other, then we should get similar values out. This should be continuous. And that's differential forms. So to recap everything that we talked about, we very lightly covered all of this material, and each one of these topics could be its own course, potentially. Like, you could study this material for a very long time and still be learning things. So at each bullet point, there will be a lot of detail left out. But just some highlights for what we talked about. We covered topologies. We talked about how it is a choice of open sets for any space that contains points, right? That's what a topology is. When we make that choice, homeomorphisms preserve the open sets. They are continuous in both directions, and they are bijective. And so any property that's defined in terms of open sets of X is going to carry over as a property that applies to open sets of Y. And so we care about the kinds of properties that that are only defined in terms of points and open sets that contain them, like connectedness and compactness, and local compactness and paracompactness. Once we define those kinds of things, we call them topological properties, and these are the things that are preserved. And we want a couple of specific topological properties for manifolds. We need it to be Hausdorff. We need it to have a countable basis. We need it to have a homeomorphism we need each point to have a neighborhood that is homeomorphic to Rn. These are the properties that make it feel like real space and makes all of the tools of analysis. It makes calculus work nicely on manifolds, and it makes the differential geometers very happy. Importantly, just to reemphasize this, homeomorphisms preserve the properties that we chose for a manifold. We only chose topological properties for how we defined a manifold. There are other properties of manifolds that are geometric in nature, but we didn't really work with any of those. Manifolds can be embedded in real space if we use enough dimensions. That's a nice property, and it can sometimes help us understand what we're actually working with when it comes to tangent spaces. But also, tangent spaces are an intrinsic part of studying manifolds. We can just describe them with their own algebraic objects. We just associate a vector space called the tangent space to each point of the manifold. That's something that we can do. And if we make one choice of a vector from each of these tangent spaces, we then define a vector field on that manifold. This is a section of the manifold that consists of all of the tangent spaces across all of the points in the manifold, the disjoint union of all of the tangent spaces. A section being a choice of just one of these vectors for each p. And again, ideally it would be continuous so that we could have a continuous vector field. In the scope of linear algebra, we can also associate to each point the vector space of k covectors, and it's denoted in this way. And these are going to be the tensors that eat k vectors from the tangent space and then give us a real number output. Right? And that has the structure of a vector space. We can associate that vector space to each, we can associate such a vector space to each point of the manifold. Right? When we do that, if we make a continuous choice of k-form for each of these points, then that defines a differential k-form on our manifold. And another way of articulating that, this is a section of the manifold of all k covectors across the tangent spaces of X. So this is denoted in this way. This is the large structure that we're dealing with, that we are choosing these k covectors from. And we are assigning one of these to each point P, just one of them, from the corresponding tangent space. Well, from the k covectors from the corresponding tangent space. And that's a wrap. That's everything. Hopefully this was informative, and hopefully we touched on enough material that this is useful for understanding the lectures that come after. Everybody have a good conference.